Hi, my name is Carolyn Straub, and I am a second-year graduate student in Andrew Riley's lab at UIC. And this is my first MIKI. I'm very excited to share with you my project, which is called the synthesis of aristoquinoline. Aristoquinoline is one of the main alkaloids found in Aristotelia chilensis, shown here, which is a plant found in South America. And it's been used as an ethnobotanical plant by indigenous peoples for many, many years. It's used for a wide variety of medicinal purposes, and the structure of aristoquinoline is shown here. But the reason why I'm interested in this in particular is because a 2019 paper by Arias and others showed that aristoquinoline is an antagonist of the nicotinic acetylcholine receptor and is specific for a subtype of nicotinic acetylcholine receptor called alpha-3 beta-4. This is very interesting because other selective antagonists of alpha-3 beta-4 have been shown to modulate drug-seeking behavior in rodents. So our hypothesis is that because aristoquinoline is also a selective antagonist of alpha-3 beta-4, it may also have these anti-addictive properties. So my group has completed the first synthesis of aristoquinoline ever published, and I want to, in particular, draw your attention to this green square step, which is a very interesting bridged Ritter reaction. So normally Ritter reactions take a nitrile and afford an amide at the end. However, this Ritter is unique in the fact that it does, there's a cyclization event that occurs to afford this amide here. And then this can later be reduced to aristoquinoline. But because the chemistry of this Ritter reaction is so interesting, and also because it yields such a unique and complex mixture of products, I've really been focusing in on this Ritter step and learning more about it. So I have purified and characterized 3 products from the Ritter, shown here, the amine, the isoamine, and the amide. Because of we suspect it has a unique mechanism, I've been doing mechanistic studies with, instead of the sulfuric acid shown here, using deuterated sulfuric acid. And so if I'm trying to learn about the mechanism between the formation of the amine versus the isoamine. And there are 2 mechanisms that I'm considering. One is a concerted 1,2 hydride shift mechanism, and the other is a non-concerted elimination mechanism. So if, while using D2SO4, the mechanism is a 1,2 hydride shift, you will have formation of the carbenium ion here, which will then either undergo reaction with the quinoline starting material, or will undergo a 1,2 hydride shift, and then will react with the nitrile and afford both the amide, or the imine, and the isoamine. However, if we have a non-concerted elimination reaction, then still we will have formation of the carbenium ion here, but then a deprotonation and elimination to form this alkene, and then reaction with the D2SO4, which will deuterate and reform this carbenium ion, which again will go on to react with the quinoline and do cyclization. And now the amine and isoamine are both deuterated. And the deuterated and non-deuterated versions can be distinguished through NMR. And when I've done this, my NMR suggests the formation of the non-deuterated amine and isoamine, which suggests a non-concerted 1,2 hydride shift mechanism. So because, like I said, this Ritter reaction forms a complex mixture of products, and the yields of these products are frustratingly low. I spent a long time trying to optimize the Ritter reaction. I tried over 60 different reaction conditions, all the basic ones that you would try, time, equivalents, different solvents, and acids, and nothing really seemed to be helping. However, I did discover that you could use a variety of different terpene starting materials. So I started with using pinene, but then quickly found that I can also use limonene and alpha terpineol. And not only is it completely possible to use a variety of different terpenes, actually the limonene produced a increase in the yield of both the amine and isoamine. And also one of the beautiful things about this Ritter reaction is the fact that the crude mixture of products, when looked at with proton NMR, you can see characteristic peaks of each of the products and the nitrile starting material in the crude, which allowed me to determine the yields of each of the products and the percent conversion of the starting material without actually having to purify each of these at with each reaction. I can just take an NMR of the crude mixture with the internal standard and find the percent yields from there. So in conclusion, my group has established the first ever synthesis of aristoquinoline, which employs this unique Bridge-Ritter reaction. And then I optimized this reaction using over 60 different reaction conditions and analyzed these crude mixtures through NMR. And currently I'm working on this mechanistic studies. I told you about one using D2SO4. I'm also working on another that isn't complete yet with deuterated terpineol. Thank you if you have any questions.
Hi there. That was very interesting. Thank you so much for all the detail.
Thank you.
One question that I did have is, what can you tell me about the other alkaloids present in Aristotelia chilensis?
So there are over, I think, 70 other alkaloids that have been isolated from Aristotelia chilensis. However, aristoquinoline is unique because it is the only alkaloid known that has this quinoline ring. All other alkaloids have an indole ring at this position, so it makes it quite interesting to study.
Awesome. What internal standard did you use for the QNMR experiment?
So I used ethylene carbonate. Particularly, I chose this internal standard because it appears around 4.5, which is clearly out of the way of any other peaks, particularly the ones in the aromatic region, which are shown here. However, if I were to do this all over again, I probably would choose a different internal standard just because the ethylene carbonate required me to have a really long D1, the time of about 30 seconds, which really extended the length of these NMR experiments that I had to run. So, and just in terms of conserving time, if I had to do this over again, I probably would choose a different internal standard.
I assume you had to synthesize the deuterated terpineol yourself.
Yes, that's true. So I started with terpinolene, which unfortunately I don't have a structure of here. It's very similar to limonene, but instead of the double bond being in this position, it is between the 6-membered ring and the then 2 methyl groups. And so I start with the terpinolene starting material, and then I epoxidate it with MCPBA, and then reduce it with LAD. So when I do that, I get a mixture of both alpha terpineol, which I want, and beta terpineol, which is useless for me practically. So it's actually been kind of a frustrating process because I get much more beta terpineol than alpha. So the yields of the alpha terpineol are pretty poor.
I see. That's really interesting. Thank you. One last question. What methods have you used to characterize the aristoquinoline you synthesized?
So this is actually a very exciting recent development. My partner on this project, Malika Arguday, she's been working on figuring out the stereochemistry of aristoquinoline and also fully characterizing it. So she has previously done a number of 2D NMR experiments, such as COSY, HMPC, HSQC, and just recently, like within the last week, she got a crystal structure of aristoquinoline, which is very exciting.
Awesome. Thank you so much.
Thank you.